Hey everyone, welcome to our next section as we start to go through angle properties and connect that to our law of sines and cosines section. So as a little warm up here, I'd like for you to find the measures of the angles that are there, 1, 2, 3, 4, and 5, and if you can, justify your reasons as to why each one is what it is, using the terminology that we discussed in class from before. So pause the video, give it a try, and come back when you're ready. Alright, so stating the angles that are here, we have angle 1. It's going to work out to be 68 degrees, and that's because we have straight lines that add up to 180, so angle 1 is 68 degrees, and the justification for that, or the reason for that, would be that they're supplementary angles. Angle 2 is opposite of angle 1, or it's supplementary to the 112. So we could either say it's the opposite, or we could say that it's because they have to add up to 180 again. So angle 2 is also 68 degrees, and we can say that that's supplementary, or it's opposite, and both will work. Angle 3 is going to work out to be, again, 68 degrees, and if you can see the C shape that's actually made there, I drew F, but if you can see our C shape that's there, we know that those add up to 180, and so if we have 112, then angle 3 must be 68 degrees as well, and those are interior angles, interior supplementary angles. Angle 4 is just opposite opposite the 60, and so it's a straight line, and so that one would just work out to be 120 degrees, and that one's supplementary, adding up to 180 degrees. And angle 5, you could probably get there a couple of different ways. The easiest way that I see right off is once you know angle 2 is 68, then it just makes this backwards F. That's right there. And so angle 5 would then be 68 degrees, and that one is corresponding angles. So just a quick recap to what we did dealing with angles before we get into this law of sines and cosine stuff. So in our unit coming up, in this unit, we're going to use the sine law to determine side lengths and angle measures in acute and obtuse triangles. We're going to use the cosine law to determine side lengths and angle measures in acute and obtuse triangles, and then we're going to solve some word problems that can be modeled using those triangles. So in order to get there, we really need to kind of go back and talk about in grade 10 a little bit, just going through some of the things with trig. So we would have studied primary trig ratios and solved problems involving right triangles, and so really this is meant as kind of a review for that. So in grade 11, we're going to explore these oblique triangles, derive the sine and cosine law. We're not going to worry too much about that ambiguous case right away. So first though, let's just go through a quick review. So to start off with, we need to know kind of what each thing means. So I've got hypotenuse, adjacent, and opposite. And so let's say that our angle was right here. I'm going to use theta. Theta, a letter in the Greek alphabet, it's used to mark an unknown angle, much like x gets used in algebra. So we have hypotenuse, adjacent, and opposite. So pause the video and just connect the word to the phrase beside it, and then come back when you're ready. Alright, so we have beside or next to, we have directly across from, and we have the side opposite the right angle. So here's our right angle, and the side opposite the right angle, hopefully you connected to be the hypotenuse. So hypotenuse is always opposite our right angle. The beside or next to part is adjacent, so we normally just put ADJ for adjacent, and then the opposite side would be directly across from. Now, in all of these cases, this is from the reference angle. So here my reference angle, my theta, is down in the bottom left-hand corner, and so directly across from would be the opposite, and the longest line is the hypotenuse, and then the adjacent is the beside or the next to the angle, next to the reference angle. What's important to know here is that if I were to switch this, and I were to put my angle up on the top instead, my hypotenuse actually doesn't change because it's just opposite the right angle, but my opposite and my adjacent do change because they're only there relative to the angle that we're using. So if I'm trying to find the angle up on the top, then opposite that would be on the bottom now, and adjacent would be on the right. So I've got a couple here. I'm just going to put thetas in their corners. I'd like for you to jot down each triangle, pause the video, and just label out relative to these angles where the opposite, the hypotenuse, and the adjacent are. So just sketch out the 4 triangles and label opposite, hypotenuse, adjacent for each one. So pause the video, give it a try, and come back when you're ready. Alright, so, and just kind of running through these, top left corner, so I've got my reference angle up on the top, which means that the opposite is the one that is not touching either line that's connected to the angle. It's the opposite from the angle. The adjacent is the side next to, and then to wonder which side is the adjacent, well, the hypotenuse is always the longest line in the triangle and always opposite the right angle. So in this case, hypotenuse would be opposite the right angle, which means adjacent is my one left over. Same thing over here, I've got opposite the angle. Hypotenuse is the longest line that's there, opposite the right angle, and then adjacent is next to the angle, next to the reference angle. Hypotenuse, adjacent, opposite. Same as the last one, opposite, hypotenuse, and adjacent. So hopefully you didn't have too many difficulties with those, just kind of labeling out where they are. Because really if you can do that, then there's no problem in going through and doing some trig. So these trig ratios, they're comparisons of length of sides in right triangles. So really a trig ratio just compares 2 side lengths, and specifically all of these work in right triangle situations. So there's 3 primary trig ratios, and one's hopefully that you'll have memorized or be able to recall pretty easily. So we've got our sine trig ratio, it's opposite over hypotenuse. We have our cosine trig ratio, adjacent over hypotenuse, and we have our tan trig ratio, opposite over adjacent. So if you look on your calculator, on your scientific calculator, you should see buttons that are sine, cos, and tan. And not only that, but ones that we're going to need after, actually above sine, cos, and tan, you should see sine, cos, and tan again, but with these -1s as exponents. They're inverses. So an easy acronym that people tend to use to remember these, and I have them all written as capital letters here, but sometimes you'll also see them as lowercase letters, okay, is SOHCAHTOA. So the S just stands for sine, the C stands for cos, and the A stands for tan. Okay. And so really if I want to put cos out, I guess I should say the full word for it, which is cosine, but it's often just written as cos. Now, if I want to see kind of what each of the other letters mean, well, to find sine, it's just the opposite over the hypotenuse, which if I go up to my equation, then I can see here that sine is opposite over hypotenuse. That's the SO part. Then CAH, the CA part, would be adjacent over hypotenuse, and if I go up to my cosine part, then I can see that it's adjacent over hypotenuse. And then the tan would be opposite over adjacent. And when we say over, remember really this is a division here, right? So opposite over adjacent. So SOHCAHTOA is going to be really important, and the big exception here is that it has to be a right triangle. Okay, that's the only way that SOHCAHTOA works, has to be a right triangle. So we have angles of elevation and angles of depression. Try not to let them confuse you too much. Basically, it just means from a certain reference point, it's looking down or looking up. The angle in which your line of sight changes as you raise your eyes to see something above you or below you. So if you're a plane, for instance, a passenger plane, as the plane's moving straight forward, maybe they take a look down toward the ground to see a tree, and so it just measures that angle that's here. Whereas a person on the bottom down here has to look up to see somebody there. So an angle of elevation, somebody below is looking up to something. An angle of depression, somebody at the top is looking down to something else. Now, what's I guess important to know here is that if both people are looking in a straight line, then we have these lines are parallel to each other, and so the angle of depression can actually equal the angle of elevation because we have these alternating interior angles that we talked about from our last unit, which makes this Z shape. So that's the reason why the 15s are the same up on the top. It's because we can assume that the line of sight from the plane is parallel to the ground. So what do we notice about angles of elevation and depression? They're equal as long as we have parallel lines. An oblique triangle is anyone that's not a right triangle. And so with these ones, I actually can't use SOHCAHTOA. I have to come up with a different way to solve these questions. And that's really where our law of sines and cosines kind of come in. So it could be an acute triangle, all three angles of the triangle less than 90, or it could be an obtuse triangle where one of the angles is really large, greater than 90 degrees. Okay, so obliques just means something different than a 90-degree angle. So solving oblique triangles, that's where we end up using our law of sines and law of cosines. But before we get there, we need a little bit of practice going through some of the stuff with our trig ratios.